Hi guys, good afternoon. Today let's continue with Lab 5 in efficient algorithms. And if you have a session with Mansa ma'am, that will be continued tomorrow morning, it seems. Vishwa sir told me to inform this just now. So today let's continue with Lab 5, which is, one second, developing a program and measuring the running time for estimating single source shortest paths with greedy method. Okay. Actually, developing a program to estimate a single source shortest path using a greedy method implements an algorithm called Dijkstra's algorithm. It's called as Dijkstra's algorithm. And what we do there is we iteratively update the shortest path from the source that is given. If we have in a graph, if we have six vertices, he'll give us a vertex and ask us the shortest path from the given vertex to all other vertices. There may be different paths, right? From A to D in yesterday's, if you remember in yesterday's graph, we have 1 minute, I'll share it. I saw this graph, right? In this graph, from if the source vertex is A to D, I have several different paths, right? I can go to D from like A, F, C, D, or A, C, D, or A, B, D, or A, B, E, D, or A, F, C, B, E, D. And we cannot say which is the shortest by just seeing the number of edges because this here I don't have any weights, but let me add some weights. A to B as 5 and A to D, A to F as 1, F to C as 1, C to B as 1, B to E, B to D as 5, B to E as 1. If you see here, now I have different weights for each edge. And if I start from A, there are different paths. Let's see which one will be the shortest. If I consider AFCD, it is 1 plus 1, 2, 5, 2 plus 5 is 7. That is 7. And if I select A to C and C to D, that is 10. If I select A to B, 5, B to C, 6, 6 C to D is 5 again, 11. It's 11. But what will be the shortest path? A to F, F to C, C to B, B to E, E to D. That is 1, 2, 3, 4, 5. That is the shortest path. But if you see that has so many edges. So one clarity that we have to keep in our mind is it's not we cannot directly say that if the number of edges that are connecting our um, source node and the final node are less, that doesn't mean that it can be the shortest path. It depends on the weights. So for Dijkstra algorithm, there are few certain rules that we have to follow. We'll start from the source node and we want to find a route to the final node, uh, which has the shortest edge weight, right? So Dijkstra's algorithm maintains a set of vertices whose shortest distance from source is already known, and every time if it finds a distance which is less than it, it will update it. It keeps on updating it. So after finishing all the process by visiting all the nodes, we will finally have a set of distances from the source node to every other vertex, which has a least distance that can be traveled. So we will simply use. Uh, I'll tell you the steps that we have to follow. and then we will first see it on paper and we'll try to convert it into an algorithm. So first we have to set distances of all vertices as infinity, and after that, because we don't know the what is the shortest distance to each node, so we'll keep them as infinity, and the source node which we are starting will keep the distance of it as 0, because traveling from the same node to itself is 0. And we'll choose the unvisited vertex which uh, which is connected to the uh, source vertex, which has the shortest distance, and we'll keep on repeating this process till we go to a dead end or till we visited all the nodes. And after that, we'll keep on whenever we'll find two or three different routes to a vertex, and we'll choose the path that has the lower distance, and we will maintain a dictionary, or will maintain a separate list which will hold the minimum, the shortest path and the minimum distance to that vertex from the source node. We'll keep on repeating this process till we visit all the nodes that are in the graph. Give me 1 minute. I'll join my phone. We'll work them. We'll try to apply this on an example. Then we can clearly understand it. I think now you can see my screen. Sorry for the delay. Let's take a random graph. First, I'm taking an undirected graph. Sorry, A, B, C, D, E, F, G, H, and I. This is a random graph. Let me add. This is an undirected graph. Let me add some weights to it. Okay. So, what is the first rule? I have to, if I'll take A as my source, I have to update A distance as 0 and all others distances as infinity. That is my first step of following Dijkstra's algorithm. So, actually, the distance of B, whenever I say distance of A or distance of B, that indicates the distance from A to B uh, till now that we have no. So initially I don't know what is the distance from A to B or A to I, the shortest distance from A to I. I don't know what is the shortest distance, so I'm simply keeping it as infinity. So now I have to visit the nodes which are connected to A, and every time when I am calculating the distance, I'll simply if I'm calculating the distance from U to V, I'll say distance of U plus cost of U to V. Cost is nothing but the edge weight. And if it is already less than the distance that is present, then only I'm updating because I want the shortest path. If there is a if there is a path to E, if there are two paths to E from A, I'll choose the shortest path, right? So this condition makes sure that we are choosing the shortest path which has less distance. So let's also write a table here. A is my source, right? And I have this will make it clear. So all the distances are infinity except A, my source. Now I'm updating A to B. What will be the distance of A is 0. A to B. I'm calculating A to B because these are connected. 0 and the cost is 4. And the distance of B is infinity. 4 is less than infinity, so I'm updating it as 4. I'll update the distance of B as 4. Similarly, I'll update the distance of C as 8. And the rest of them, I don't have the path. So there will be infinity itself. I don't have the path to any other vertex from A. I have only a path to B and C from A. Which one is less here? 4 is less. So I'll select 4. And uh, A is my source path. So I already visited it. So I'm canceling it. And C is I'm selecting B because it has the shortest path. So B is also already gone. And I'm updating C's distance. This is also already visited. So now I'm selecting other paths. From B, I have path to A, B, and D, right? So A is already selected. I have removed it. B is already selected. It's gone. So I have path to D and C from B. So what now distance of B is 4. If I calculate B to D plus the uh, the edge weight is 8, which is 12. 12 is less than infinity. So I'm updating these distance as 12 here, and these C's will be 8 only, because if I calculate B to C, what will be the distance from B to C? B's distance is 4 plus B to C, it is 11, which is 15. Here it's not infinity. I have D's weight as 8. No, this is false, so I'm not updating it. It will be 8 itself, right? And I don't have path to others. I have path to A, C, and D from B. A is already selected, so I'm removing it. But C and D, I wrote it. So all the rest of them will be infinity. And out of this, C is less, so I'm selecting C. Now C is also visited. From C, I have path to A, B, E, and F. So I'm calculating A and B are already visited, so I'm calculating for E and F. So for E, it will be 8 plus 7, 15. And for F, it will be 8 plus 1, 9. Now 9 is smaller, so I'm selecting 9. This has 9, E has 15, right? Yeah, that's it. From I selected F now. From F, I have path to C, E, and H. C is already selected, so I'm removing it. Uh, for E, it is 9 plus 6, that is 15, which is the same, uh, uh, which is the same as that is already present 15, so there is no need to update it. And for H, it is 11. For H, it is 11. It's 15, 8, yeah. And this one is 15, it is already equal, so I need not update it. It is 15. Even in that case, H is 11, so I'm selecting H. And from H, if I see, I have path to D, G, and I. For I, it is 20, it will be 21, which is 11 plus the distance between this, which is less than infinity, so it is 21. And for G, it is 11 plus 14, which is 25. And for D, it is 11 plus 4, that is 15. So what is the shortest path in these three? 15 is the shortest. So I'm selecting D. So from D, I have uh, paths to E, G, and H, and B also. But B and H are already selected. That means I have path to E and G. I'll calculate it for E and G. Uh, for E here, it will be, this is 15 now. 15 plus 2, which is 17. But E has 15, right? Which is less than 17. So we need not update it. We are not updating it. It has 15 only. We are not selecting that part. But from uh, D to G, it will be 15 plus 7, that is 22, which is less than 25. So I'm updating it. Out of these two, 15 is less, so I'm selecting 15. Now from E, I have path to C, F, H, and D, but all of these are already selected. So I'm randomly, I have to select uh, G or I here. Because those are the only two that are vertices that are left now. G has the weight 22 now. I has the weight 21 now. Which one is less? 21. So I'm selecting I. And from I have path to G that will be 30. But G already has 22 as the weight, as the distance. 30 is greater than 22, so I'm not updating it. So it will be 22. Now, if I write, all these are calculated from A, right? And A, B, C, D, E, F, G, H, I. So for A, it is 0. A to A is 0, the minimum distance. A to B is 4, that is the minimum distance. A to C is 8, that is the minimum distance. A to D is 12, that is the minimum distance. So I tried. A to E, 15, that is the minimum distance. A to F, 9 is the minimum distance. A to G, 22 is the minimum distance. A to H, 11 is the minimum distance. A to I, 21 is the minimum distance. So by following Dijkstra's algorithm, we can say that uh, if the source vertex is A, we can find the minimum distance to each other vertex in the graph. Now, this can be done for uh, directed graph also. But here we have to keep in mind that we cannot select all the matrix, all the vertex that are neighboring, right? What is the difference between an undirected graph and directed graph? The neighbors will change. In an undirected graph, all the will think that there is a path from D to E and there is also a path from E to D. But in a directed graph, this arrow mark will indicate that there's a path between E, there is a path from E to D, but there is no path from D to E. So we have to keep this in mind and we have to follow the same procedure. Let it be like this. I'll take random numbers. My source is A only, and A, B, C, D, E. A, I'll keep 0. All the rest of them will be infinity. I'm selecting A, and from A to B, my short will be 6. A to C, it will be 5. I'm selecting C because that is shorter. From C to B, it is 3 plus 5, that is 8. But 6 is already less, so it will be 6 only. And from C to D, it is 5 plus 2, that is 7. Before it is infinity, now it is 7. 7 is less than infinity, so I'm updating it. And after this, C to E, it will be 6. 6 is less than infinity, so I'm updating it. Now we can either select B or E because both are same. Let's select E. This is 6. C is 5. And from 6, I have only path to D, that is D has 7 now, which is equal to 7. So there is no need to update. Even in this path, the weight of the path is 7 only. And I have no other way from this. I have to select this. And from D, I don't have any other path, right? There is no way from D to B. So fine, in the end, I'll select B because I have to visit all the nodes. We have to keep an eye on that also. All the nodes, all the vertices should be selected at least once. Now the shortest path will be 6 from A to B, 5 from A to C, 7 from A to D, 6 from A to E. Sorry, I think this is 7, right? 6 here plus 1. It is 7 from, yeah, A to E. Actually, we can also know the path with this table. The use of this table is, if I want to find the path from A to D, I know the distance. You're saying that the shortest distance from A to D is 12. But what is the path? There will have so many paths from A to D, but how are you saying that this is the shortest path? So if I go from back here, whenever it is changing, I have to see what did I select. Here it is 12. From infinity, it became 12, right? So I'm seeing what did I select here? I selected B. So from D, I selected B, and from B, it changed here. I selected A. So A, B, D is my shortest path. And what is the distance? 4 plus 8, 12. If we see for I, let's say see it for I. A, what is the shortest path between A to I? First, I took I, the shortest distance, I'm saying it as 21. But where did it change? It changed here. I selected H here. It changed here. I selected F in the above row. And in the above row, I selected 8. That is C, right? And in the above row, I selected B. And in the above row, I selected A. So the path from A to B is A, B, C, F, H, I. This is the shortest path. A, B, A, sorry, A, B, C, F, H, I. This is a little bit messy. Please try to see it. A, B, C, F, H, I. This is the shortest path. I have all other elements here. This is the shortest path. And what is the distance? 4, 11, 1, 2, 10, right? If I add them, 15, 16, 17, 18. This is 1 or 10. H and I. Right? 15. From H, it is 11 plus 10 is 21. Yeah, till H, it is 11, right? 8. Okay, this is B or this is B. We made a mistake somewhere, but if we consider this as B, we took this as B, right? 8, 9, 10, 11 plus 10, 21. We took this as B. We did a calculating mistake here because this is 8, A, 8. We selected it like this, where this is 8, 8, 1, 2, and 10. This becomes 21. Yeah. So it is the same for the directed graph also. Every time when it changes, we have to see the path from backtrack. Now see this. This is a random graph. This is the given graph. First, I'm taking the distances of each vertex as infinity and my source vertex as 0. Here he took D as source vertex, right? Can you see my screen now? Can you see a graph with A, B, C, D, E, F, G, a document? Okay, I'll stop sharing and again start. Can you see it now? Can somebody tell me whether you can see my screen or not? You can see the graph, right? So I'm selecting the distances of all the vertices as infinity. INF indicates infinity and 0 for my source vertex. He took D as the source vertex in this example. So after representing them, it will be like this. D will be 0 and all the others will be infinite. So now he is checking for all the paths and calculating their distance. A becomes 4, D becomes 2, which is by the formula that we have seen, it is 2 plus, sorry, 0 plus distance between D and E, that is 2. So it became 2. Now he will select 2 and he'll continue the process. He'll after going to all the vertices and he'll update where only if the new distance is less than the given distance, he will update the distance of each vertex. Finally, we'll have the minimum distances from D to every other vertex. What will be the time complexity of this? We have to uh, go to all the vertices first. So for that, it will be of the number of vertices. And since we are using from that vertex, we are seeing the distances to all the vertices that are connected to the second vertex also. That will be again n. So n into n, it's like a two for loops, right? So it will be O of n square. But uh, while writing this in the code, we can select the shortest path by simply keeping a priority queue, right? Or heap sort. Any data structures which can easily sort the things in log time. So in that case, the time complexity can be reduced. But on but in the greedy method that we are following, mostly it is near to O of n square. Now let's try to write an algorithm for this. I'll write a program, extras, which will take the graph and a vertex also. Let me call it starting vertex or start vertex. And I need a graph. This is my answer actually. This is my result. This is a graph where for each node I should have a distance, right? For that means for each vertex I should have a distance. In the beginning it will be infinity. I'll simply this will store as this should happen for each vertex in the graph, in the given graph, in graph, because graph is already given. So, for example, my distances will be like this. Distances in the beginning, after this line, you know how it will be. If my graph is A to B, A to C, A to D, I'll give it a in the form of a dictionary where the it is a key value pair. A dictionary is a key value pair. The key will be the vertex and values will be it actually it is a 2D dictionary where the key is the vertex and the value is a dictionary which will indicate the distances from each vertexes to it. In the beginning, it will be like this. If I have A, B, C, D, then it will be A as infinity, comma, B as infinity, and so on. This line will be like this. The distances dictionary will be like this after this line. But my initial start vertex distance should be 0, right? So distances of start vertex will be 0. And how do we select the minimum distance every time? We can use, actually you can, with if you want to take a few more data structures, you can keep two lists, one for the distances and uh, one for its vertices like this. 1 minute. You can see, you can keep it like this, right? Now distances, I have it like this. I'm using a dictionary simply. If you, but you can also show them like this. But every time if you want to check it, what is the minimum distance? You will use a for loop, right? That will increase the time complexity. But we have inbuilt data structures for that. I mean, min heap or max heap, and actually those are already in the form of libraries in Python. So we can simply use them. So I'm going to use a heap data structure. I'll use a priority queue. PQ indicates priority queue. And I'll say that it will start from starting vertex, right? It will start from starting vertex. That is already given. Now, till there is something in priority queue, I want this leap to be continued. I'll remove each element from priority queue. I'll add them and also I'll remove them. So whenever there are no elements in the priority queue, that means that I have visited all the elements which are present in priority queue, right? So the current distance, that means every time we are selecting, if you remember, we have drawn a table, right? And e and at every row we selected a vertex, and we have the current distance to that vertex, right? So the current distance and current vertex will be the last element in the priority queue. So priority queue will be anyway sorted. So we need not sort it, right? So I can simply uh, pop it from priority queue. Heap pop is a inbuilt property. I can use it and I can pop it. Every time when I pop it, I'll get the current distance and current vertex of that graph where I'm selecting the minimum distance one because I'm popping the element. I'll get the minimum distance one. And now I have to add, now I have to push something into the heap pop in such a way that it has distances from, it has away from the current vertex to all other vertex which are not already visited, right? They should not be visited. So for each neighbor, let's call neighbor, each neighbor, comma, edge weight, it will have edge weight, right? Edge weight in, will give a graph of current vertex, right? And I don't want all other vertices. I want only wave from current vertex. Dot items. So I'll get all the items from it. The distance, I should calculate the distance, and I have to check whether it is less than the distance that is already present or not, right? What will be the distance? It will be the current distance. It is current distance of the vertex plus weight is already given here, right? The weight will get it from the edge weight. We are selecting each edge weight. So it will be edge weight. And now we have to check whether this distance is less than the distance that is already present, right? Distances of neighbor. If it is not less than, we should not update. But if it is less than, but if it is less than the distance that is already present, I have to update it. So distances of each neighbor will be my new distance because this is less than the distance that is already present. And I have to push this into the priority queue. Then only it will select for the next step. It will select the least path variable that is present. For pushing it, the method name is heap push. I'm going to heap push into priority queue. What am I going to push? The distance, the new distance, comma, the name of the vertex. It should know for which vertex it is present, right? After completing the while loop, we can just return the distances. Distances is a dictionary. So let's try to give this a graph. Graph is a 2D dictionary. Let's say I'll take A and I'll add B, C, and E. I'll say from A to B, I have a path of length 4, the edge width 4, and A to C as 1. From B, I'll say I'll I have a path to D as 3, and from C, I have path to A with 1, because this is undirected, right? If we have A to B, then I'll have B to C. If I have B to D, I'll have D to A anyways. So D to, sorry, D to B, that is 3. And I'll also add path to E. And from E, I'll just keep it like this. Let's add one more thing to this. To B, I'll have path as 5. This is my graph. I'm going to print, sorry, I'll call this function, and I'll give graph. This graph is this only, and I'll give A, and let's try to print it. How to say invalid syntax here? Let me check it 1 minute. Yeah, yeah. After every, Each neighbor is not defined. Okay, there is a spelling mistake. So it is saying that from A to A, that my shortest path is 0. From A to B, it is 4. A to C, it is 1. And A to D, it is 6. And A to E, it is 9. These are the shortest path from A. Now we have calculated, um, in an example, we have calculated, right? We'll check for that. In that graph, if you remember, there are different connections from A to B. We have few more vertices, right? To make it fast, let's simply create a, or we did it for this, right? In this case, let's find it in what we were getting. We will directly ask GPT to give it so that we can do it fastly. I want this in the format of this, right? Convert. Yeah, it gave, right. So now we can check them. This is my graph, and I'm checking from A. So the answer that I got is this. Let's check manually. So it is saying that for this graph, my shortest paths from each vertex from A are A to A to, let's check from A to D. It is saying as 10. A to D, it is saying as 10. Then I think there's some mistake here. Because A to B, it is 5. A to C is 5. We didn't add A to C here, right? We did a mistake. Let's add it manually. A to C, I have the distance as 5. So from A, I have F, C, and B. F, C, and B. To C and B, it is 5. And for F, it is 1. So this is correct. From B, I have A, C, D, E. A, C, D, E. I should add A. From B to C, it is 1. And B to A, it is 5. and B to D is 5 and B to E is 1. Yeah, so that is finished. From C, we have F, A, B, D. F, A, B, and D. C to F is 1, C to A is 5, B is 1. A is 5, B is 1, C to D is 5. Yeah, and from D, I have C, D, and E. C, B, and E. D to C is 5, 5, and 1. 5, 5, and 1. And from E, I have D and B, and both are 1. D and B, both are 1. And from F, I have A and C, both are 1. Yeah. Now we got the path from A to D as 5. A to D as 5. Even now we are getting something with a mistake, right? No, no. Yeah, that's correct. A to D, we can, the shortest path is 5. We can go from A to F 1, F to C 2, C to B 3, B to E 4, E to D as 1. So the shortest path from A to D is 5. And what is the shortest path from A to E? That is 4. A to E is 4. It's actually the same path. What is the shortest path from A to B? It will be 1, 2, 3. Yeah, A to B is 3. What if we change the vertex here? Let's change the vertex to D, my initial vertex. So now from D, my shortest path to A is 5. From D, my shortest path to A is 5. This is the shortest path. Let me take B as my initial. I think then it will change because it's like a symmetric graph, right? From B to 8 is 3 that we know. From B, let's check from B to D. It is saying us 2. From B to D, it is 2. Yeah, B, E, and D. B, E, D. This will be 2. And actually, here we used heap Q. But if you want to make this possible without using this, you can simply use like this also. Every time we have to check whether the vertex is sorted or not. Actually, I have a code for that. I'll share all the codes that I have about Dijkstra's algorithm. You can go through them, but it is always useful to use models that are inbuilt and data structures which will take less time to push or pop. So that's the reason they're created, right? If you have any doubts, you can ask me in the comment box. Sorry, in the chat box. I have sent the codes in the IPYNB file. Okay, if you have any questions, you can mail me or type them in the chat box. If you don't have any doubts, I think we are good to go. Have a nice day. Go through the codes, and I'll also send you the rules which I followed while doing this on the paper, because this recording is available in the YouTube, right? So you can go there and see the um, procedure that we have followed while solving the Dijkstra's algorithm using pen and paper. That will be very useful, because if you have the algorithm in mind, you can code it in several different ways. Have a nice day. Thank you.